Today we're going to continue talking about chemical reactions, and today we're going to talk about the 5 types of chemical reactions. And these notes start about halfway down page 10 in your packet. So there's going to be 5 different types of chemical reactions that we discussed today. And the first one should look familiar from our combustion analysis problems. So a combustion reaction is our first type we're going to discuss today. And what a combustion reaction is it's when we burn any substance, and remember it takes oxygen in order for this to happen. So we're going to burn any substance with oxygen, and that's going to make some heat. Now, usually the thing that we burn is a hydrocarbon, which we know can contain carbon, hydrogen, sometimes oxygen, sometimes nitrogen, but always carbon and hydrogen. Now, when we do this, our products are always going to be carbon dioxide and water vapor. So here you can see that general formula for combustion reaction are hydrocarbon plus oxygen, and that always makes carbon dioxide and water. And then here we have one actually written out for you. So that's CH4. That hydrocarbon is called methane. And that's methane reacting with oxygen, and it's making carbon dioxide and water. Our next type of chemical reaction that we're going to talk about is a synthesis reaction. Sometimes this is also called composition. And what a synthesis reaction is a synthesis reaction is when we have 2 or more elements or compounds that join together in order to form a more complex compound. So when we start getting into these types, there are some easy ways for us to identify what it is. And a synthesis reaction is always going to have one product. So that is our key. If it has one product, it's a synthesis reaction. So our basic form would be like some element or maybe a compound combining with an element or a compound, and that's making just this one product here. Sometimes it could be not necessarily an element, but maybe that's like a compound and another compound, and it joins together to form one more complex compound. And then in simple picture form, right, we got a red element and a blue element, and they join together to make a blue and red compound. But again, what's making it unique, how we can always identify this as a synthesis reaction, is we just have one product here. Now, some general examples of a synthesis reaction, you might have a metal reacting with oxygen, and that's producing a metal oxide. That's what we did in our empirical formula lab last week. We did magnesium. We reacted it with oxygen in the air, and we produced magnesium oxide. And you could substitute any metal. So aluminum and oxygen joining together is going to make aluminum oxide. You could also have a nonmetal joining with oxygen, and that would then form a nonmetallic oxide, like carbon reacting with oxygen to make carbon dioxide. We could also have a metal and a nonmetal joining together to make a salt. And the salt that you're probably most familiar with is table salt, NaCl. And that reaction would be sodium plus chlorine, and that makes sodium chloride. You could also have a few nonmetals combining with each other and then form a covalent compound here. So like phosphorus plus chlorine joins together to make phosphorus trichloride. So lots of different things can happen for a synthesis reaction, but notice all of these examples only have one product. That's what makes a synthesis reaction able to be recognized easily. Now, the opposite of synthesis, if you will, is a decomposition reaction. So in a decomposition reaction, we have one compound and it breaks down into its component parts of simpler compounds or elements. So what makes decomposition recognizable is we have one reactant. So we can have a basic form of just like a simple compound, and it breaks apart into the 2 elements that make it up. Or maybe we have a more complex compound, and it breaks apart into simpler compounds. Again, what's making this unique is we just have this one reactant here. So here we have this compound, right? And it's breaking apart into the elements that make it up. So let's take a look at some examples here we have of decomposition reactions. So some oxides, like this mercury oxide we have written below, when heated, they decompose. Ooh, how can we show when heated? We could put a triangle over that arrow to show that it takes heat in order to make it decompose. Some are produced by electricity. So you could have water, and if you add a little spark of electricity, which we can use a lightning bolt, it breaks apart into hydrogen and oxygen gases. Or perhaps we take that salt that we synthesized in the previous reaction, a synthesis reaction, and if we add a little spark of electricity, we could break it back apart into the two elements that make it up, sodium and chlorine. Now, starting at number 3, I want you to make sure that you put a big asterisk by these, because on number 3, we're going to have to start memorizing some of these things because they always do the same thing. So most metallic hydroxides, so if it's a metal hydroxide, when we heat it up, right, so we're going to use the triangle, they're going to decompose into a metallic oxide and a water. So a metallic hydroxide produces a metal oxide and water. So take a look at this. We could have calcium hydroxide. Calcium is a metal joined with hydroxide, so we would consider this a metallic hydroxide. When we add heat to it, what it does is it breaks apart into calcium oxide plus water. Now, sometimes because of balancing, it's easier to see is if you write the water part of it as HOH, but notice these are the same equation, right? So put a big asterisk here. We need to know that when a metal hydroxide is heated, it decomposes into the metal oxide and water. Another one we need to have memorized, so another big asterisk here, is a metallic carbonate. And when they are heated, so if we have a carbonate that heats, it breaks down into, again, a metallic oxide, but carbon dioxide. So here we have calcium carbonate, and when it breaks down, right, when it's heated up, it breaks down into a metallic oxide. And then notice this time, right, what's left? After you take away that Ca and the O, we still have a C and 2 oxygens left, which makes sense why we have carbon dioxide left. So even though they have to be memorized, if you just think about them a little bit, they do really make sense what's still there, right? If you think about calcium's gone, one of the oxygens is gone, what's left? CO2. So memorize, but also just think a little bit. And our last type of decomposition reaction we need to memorize is a metallic chlorate. And a metallic chlorate, when we heat it, it decomposes into a metal chloride and oxygen. And again, just think about this a little bit. Here we have potassium chlorate, and what it's going to make is potassium chloride and oxygen. So just take a look at that reactant, right? If I'm going to do a metal chloride, there we go, and what's left? Oxygen. And we know oxygen's diatomic and always comes in twos. So memorize, sure, or think about it. A metallic chlorate breaks down into a metal chloride and oxygen. So those are the decomposition reactions. And again, these last 3, make sure you memorize them. I'm going to say them one more time. We have a metallic hydroxide that decomposes into a metallic oxide and water. A metallic carbonate is going to break down into a metallic oxide and carbon dioxide. And a metallic chlorate is going to break down into a metallic chloride and oxygen. And those are your decomposition reactions. And how we can identify a decomposition reaction is we've got one reactant. So let's move on to single replacement. So in single replacement, what's going to happen is we have a more active element that's going to take the place of another element in a compound, and it sets the less active one free. Okay, so let's take this a little bit at a time. So first, what we're going to have is we're always going to have 2 reactants and we are going to make always two products in a single replacement reaction. But if you think about it, that was the same for a combustion, right? In a combustion, we had two reactants and two products. So what makes these unique is that it's going to be an element and a compound. And so we're going to have an element and a compound in our reactants, and we're also going to have an element and a compound in our products. So our basic form might be that we have this element reacting with a compound, and what gets produced is a compound and an element. Or maybe they switch places in different ways, right? We could have a compound and an element, and that makes a compound and an element. And right now, those might look kind of the same, but I'll show you how they're a little bit different here when we get more in depth with our single replacement reactions. So the first type that could happen is when we replace a metal in a compound by a more active metal. So here, first we can identify this as a single replacement reaction because we have 2 reactants and 2 products. And of those, we have an element reacting with a compound, making a compound and an element. That's a single replacement reaction. And what you can see here is we have iron reacting with copper 2 sulfate. And iron is more reactive than copper, and so what happens is iron replaces copper in the compound, and now copper is the free element by itself. We could also have hydrogen involved in a single replacement reaction. And in this case, it's really helpful to think of water as HOH so that you can see the replacement a little bit easier. So on this first one, I'm going to actually focus on the or way that it's written so you can see what's really happening with the replacement. So what's happening here is we have sodium reacting with water, and it's producing sodium hydroxide and hydrogen gas. And so we can identify this as a single replacement reaction because we have an element reacting with a compound, producing a compound and an element. And so this sodium is more active than the hydrogen. And so what happens is this and this switch places, and we make the sodium hydroxide, and then hydrogen is by itself, but we know hydrogen is diatomic, and so it always comes in pairs. Another example might be magnesium reacting with water to produce magnesium hydroxide and hydrogen. And in this case, that 2 just kind of skipped down to the next line. That 2's right there. Didn't forget that it was diatomic. Another example of a single replacement reaction might be if we have hydrogen and an acid replaced by an active metal. So here we could have zinc, that's an element, reacting with hydrochloric acid. And because that zinc is more reactive than hydrogen, we're going to make zinc chloride and hydrogen gas. And again, what's happening is the zinc is switching places with the hydrogen to make the zinc chloride and hydrogen gas. Hydrogen is now the element by itself. Our last type of single replacement reaction would be if we have a nonmetal that's getting replaced by a more active nonmetal. So here we could have chlorine, and chlorine's a nonmetal, right? So it doesn't want to replace the sodium part of the next compound. It wants to replace the bromine. And because chlorine is more reactive than bromine, these two are going to switch places, and now our product is sodium chloride, and bromine is the element by itself. Again, bromine, diatomic. Make sure you don't forget that when you write the equations. So how do we know whether a single replacement reaction will occur or not? Well, we have to look at the activity series, and we have an activity series for both metals and nonmetals in order to predict whether the reactions will occur or not. What we want to look at is we want to look at the free element. So that's the element by itself in the reactants. And we want to see, will it replace the element that is in the compound? And if the free element is above the element in the compound, then the reaction will occur. But if that element by itself is below the element in the compound, then no reaction will occur. And this is because a more reactive element is more likely to participate in a chemical bond. So let's take a look at the activity series. So up top here, we have the activity series for the metals. And also included on this list is hydrogen. And that's because hydrogen acts like a cation, right? Hydrogen likes to form a positive ion, just like the metals. So metals are going to try to replace hydrogen, where hydrogen is going to try to replace metals. Down here, we have our reactivity series for our nonmetals, which if you look, is really just the halogen group. So let's take a look at an actual problem here. What we want to see is, will the free element, the potassium that's by itself, replace calcium, which is the metal inside the compound? So if we take a look at the activity series, potassium is up here and calcium is below it on the activity series. So because potassium is more reactive, it's above calcium, this reaction will occur. So let's figure out our products. These two are going to swap places, and now potassium is going to be bonded to chloride, and because potassium is +1 and chloride is -1, that compound is going to be KCl. And then the calcium is now going to be the element by itself, or the free element. After we predict those products, we then need to balance the equation. And because I have 2 chlorides in my reactants, I'm going to need to put a 2 in front of the potassium chloride in the products. And then because I put a 2 there, I need a 2 there to balance this reaction. Let's take a look at another example. So for the second example, I have gold. Gold is our least reactive element, and it wants to try to replace strontium. Ooh, strontium is very reactive. So gold, the element by itself, is below strontium, so this will not happen. So we can write no reaction. And why this is because since gold is less reactive, it is more likely to be found as a free element than strontium, which is more reactive and therefore wants to form bonds. Let's try an example with our nonmetals. So here we have sodium chloride and fluorine. How I know this is going to be our nonmetals is because fluorine is the element by itself, and it's going to try to replace chlorine, which is the element in the compound. And in this case, fluorine, the element by itself, is above chlorine, the element in the compound, so this reaction will occur. For our products, we're going to make NaF, and because Na is +1 and F is -1, that's just going to be NaF. Then for our element by itself, I ran out of room here, so I'm going to put it right underneath. We're going to have chlorine. But remember, chlorine is a diatomic element, so it's always going to come as Cl2. Then we need to go back and balance the equation, which should be pretty simple because we have 2 diatomic elements here. All we're going to need to do is put a 2 in front of the sodium chloride and a 2 in front of the NaF to balance this equation. Okay, our last type of chemical reaction we're going to talk about is a double replacement reaction. And we're going to go into more in-depth notes on double replacement reactions later on in the unit. But for right now, what we need to be able to do is recognize a double replacement reaction. So a double replacement reaction is when we have ions in 2 compounds that are changing partners. So the cation of one compound combines with the anion of the other. How we can recognize a double replacement reaction is we're again going to have 2 reactants and 2 products, which is very similar to a single replacement reaction, but in a double replacement reaction, it's all compounds. So if we see 2 reactants and 2 products and everything is a compound, we know it's a double replacement reaction. And this happens always in an aqueous solution, which just remember means something dissolved in water. And a reaction will occur when a pair of ions come together, and what they produce is possibly a precipitate. Remember, that's a solid. Perhaps they come together to form water, which would be a liquid, or perhaps they come together and form some gas. So our basic form here, we can see we have 1, 2 reactants and 1, 2 products. And they are all compounds, right? They contain 2 letters here. We could have more complex, right? Compounds with maybe a polyatomic ion involved, but we can recognize a double replacement reaction because we have 2 reactants and 2 products that are all compounds. Let's take a look at the solubility rules for double replacement reactions. So for double replacement reactions, in order to figure out whether they will occur or not, we need to use the solubility rules in order to do so. The solubility rules are going to determine whether the product is insoluble in water. So we're looking for something insoluble, and that insoluble thing is going to be our precipitate, because remember, our precipitate is a solid. If the compound is soluble in water, then it should be shown as aqueous, and if both products in the solution are soluble, then no net ionic reaction occurs. And we'll go into more of this left as separate ions and this no net ionic reaction more in our next set of notes. But let's take a look what we need to know in this set of notes. So here are our solubility rules. Our solubility rules will always be given to you on every test and quiz. They don't need to be memorized until AP. And what we can see is that an alkali metal, so remember alkali metals are that first group on the periodic table, so like lithium, sodium, and so on, those are always soluble. It does not matter what anion they're bonded to. If it's bonded to an alkali metal, it's soluble. And the same can be true for ammonium. Ammonium, no matter what it's bonded to, is always soluble in water. So alkali metals and ammonium will never be the precipitate. The other thing that will never be the precipitate is anything when it's bonded to an anion of nitrate, acetate, or chlorates. Those are always soluble with no exceptions. Let's get into some of the rules that are a little bit more complicated. If something is bonded to a chloride, a bromide, or an iodide, it's soluble, unless that thing is lead, silver, or mercury. So for example, silver iodide is going to be an exception and it's going to not be soluble. So silver iodide would be our precipitate because it is insoluble. Other things like sulfides are always insoluble unless it's bonded to a specific cation like ammonium or alkali metals or even alkaline earth metals. Remember, alkaline earth metals are like calcium, strontium, barium, and so on. So let's try one of these. So our 2 reactants are sodium chloride, which is aqueous, and silver nitrate, which is aqueous. Now our reactants should always be aqueous, but look at the rules to see why. Here we have sodium chloride. Sodium is an alkali metal, always soluble, no exceptions. In order to show that it's soluble in our state of matter, we write AQ. AQ means dissolved in water or soluble. Next, we have silver nitrate. So this is a nitrate, and as you can see, the nitrates are soluble with no exceptions. Therefore, silver nitrate is also aqueous. Now, for our products, what we're going to do is we're going to take that sodium and silver, and they're going to switch places. So sodium is now going to be bonded to nitrate. Because sodium's +1 and nitrate's -1, our first product is going to be NaNO3. Our second product, which I'm going to write just below here, is going to be silver. Silver is always +1, and it's going to be bonded to chloride, which is -1. So the formula there is AgCl as well. Now let's look at our solubility rules. So this first thing is, again, sodium, which is an alkali metal, soluble with no exceptions. You could also look at the nitrate part. Nitrates are soluble with no exceptions. Therefore, for sodium nitrate, I'm going to write AQ because that is soluble and not our precipitate. Let's take a look at the other thing. The other thing is a chloride. Chlorides are soluble except silver. Therefore, this is insoluble, and we mark that with an S for solid. So our insoluble thing is our solid thing. So if we needed to determine the precipitate, this solid thing right here, silver chloride, that is our precipitate. So this is a double replacement reaction that will occur because we made a precipitate.